continuing on with writing quadratic equations given the roots or solutions. This example says, find the formula in standard form y equals ax squared plus bx plus c for a quadratic that has roots at x equals 3i and x equals negative 3i and has a leading coefficient of 1. Alright, so this is the same type of problem, it's just now we have a complex solution. So again, starting with that x equals 3i, we have to get everything on one side and set it equal to 0. So now this says x minus 3i equals 0 or x plus 3i equals 0. Working that zero product property in reverse, these are the factors in our quadratic equation. And to get it in our standard form, we need to multiply that out. It's just 2 terms by 2 terms, so I'm going to use the box method. You could also FOIL. I have x minus 3i and x plus 3i. X times x is x squared. X times 3i is 3i times x. And negative 3i times x is negative 3ix. And lastly, negative 3i times a positive 3i is negative 9i squared. Don't forget that square. I times I is I squared. I notice I have 3ix and a negative 3ix. Those add up to 0. So what's left is x squared minus 9i squared. But we don't leave I squared. We know that I squared equals negative 1. So we're going to replace I squared with negative 1. And negative 9 times negative 1 is positive 9. Whoops, not x. That should be 0. And now it's in our standard form. Notice we ended up with a sum of squares. Sum of squares is not factorable. It won't give us real number solutions. It'll give us imaginary solutions. And actually, I just realized we don't want to leave it in this form. We want y equals. So I actually need to write this as y equals x squared plus 9. This will be a quadratic equation of a parabola that will have those roots. Alright, go ahead and try the example on the right hand side. It will be more intense because it has 2 plus the 5i and 2 minus the 5i. It'll end up being a little bit more like this other example we did in a previous video, but go ahead and try it out and see how you do. Alright, example on the right. Find the formula in standard form y equals ax squared plus bx plus c for a quadratic that has roots at x equals 2 plus 5i and x equals 2 minus 5i and has a leading coefficient of 1. Alright, so just like we did before, we're going to set these equal to 0. That means we would subtract 2 and subtract 5i from both sides on that first solution. And we would subtract 2 and add 5i on the second solution. Right? I'm just taking these solutions and setting them equal to 0. Those become our factors in our quadratic equation. And to actually solve that, or not solve it, but simplify it into our standard form, we have to multiply that out. Again, I like the box method to keep track of all my terms. These are 3 terms by 3 terms. So I'm going to make it kind of big. And each term is separated by a plus or minus. So x minus 2 minus 5i, and then x minus 2 plus 5i. First row, x times x is x squared. Negative 2 times x is negative 2x. 5i times x, I can just write 5ix. Negative 2 times x again in the second row. Negative 2 times negative 2 would be a positive 4. Negative 2 times 5i is negative 10i. Last row, negative 5i times x is negative 5ix. A negative 2 times negative 5i is a positive 10i. And lastly, 5i times a negative 5i. Remember, we're multiplying, not adding. Sometimes I see students write 0 here, but we're multiplying, so we get negative 25i squared. Don't forget that I squared. Alright, I evaluate before I'm going to write stuff out. I see I have a 5ix and a negative 5ix. Those will add up to 0. I have negative 10i and a positive 10i. Those will add up to 0. Let's see what we have left. We have x squared, negative 2x and a negative 2x, a positive 4, and a negative 25i squared. I need to simplify all this. I see I've got some like terms. So negative 2x minus 2x is minus 4x, not 0, right? They're the same sign. We add them, keep that sign. Plus 4, and I squared is the same thing as negative 1. So we replace I squared with negative 1. And then, oops, it's an x. Negative 25 times a negative 1 is positive 25. And I should have added this. Everything is still equal to 0. And then I add that 4 and 25. And I get 4 plus 25 is 29. Now we want to write it in the form y equals that quadratic that we found. And there you have it. If we were to solve this for the x-intercepts or the roots of that quadratic equation, we should get 2 plus 5i and 2 minus 5i. There you have it. So essentially we're just working that solving in the reverse order to get back to the equation that you would have started with.